Penguin, and this is my report for Lab 2. So the purpose of this experiment is to demonstrate the motion of a falling object under the effect of gravity and drag. This examines the accuracy of Newton's second law and how opposing net forces affect the velocity, acceleration, position of a falling object in motion. So to test this accuracy, graphs of vertical position of time versus time for both the observed and simulated models are compared, and we'll see that accounting for all these forces verifies Newton's second law. So the momentum principle describes how the net force acting on a system creates a change in momentum over time. Therefore, we can use these formulas. With this principle, the two formulas necessary for this lab can be derived, which are the velocity update and the position update formulas. And we can say that for small delta t, the v average is approximately the same as v current, which is why we can use this formula. So since a falling object speeds up from rest after it's dropped, there has to be some net force, as indicated by Newton's second law. So one has to be the attractive force of the planetary body in the surroundings. We know that Earth exerts a constant downward force of gravity. However, in real life, falling objects don't generally have constant acceleration, which means that there has to be some other force acting on the system. And this other force is air friction or drag, which is proportional to the square of speed and acts opposite to the direction of motion, opposing gravity. And it's important to note that this is not a constant force because the force of drag will change as the velocity changes. Before tracking the motion of the chosen object, I calibrated the tracker software and then marked each frame to track the position. And the data obtained by this creates initial conditions for these simulations. So here we just have a video of the tracker software. The coordinate axes are oriented such that it's tilted to correct the tilt of the video, and the origin is set at where the ball is dropped. And we can see that there's a negative acceleration in this position graph. So using the data from the tracker program, we can create initial conditions for the computational models, including the net force for gravity only, which would be just negative mg, and the F net for gravity and drag would be the force of drag plus the force of gravity. And it's important to note that the system is the tennis ball and the surroundings are the floor, earth, and air. So here we have an initial y position, an initial time, and these were just pulled from tracker. And since the object starts from rest, we can say that the initial velocity is 0. So in the gravity-only model, we can use the formulas derived earlier to represent them in code. Also, the net force can be set to equal the mass times the magnitude of gravity times the unit vector in the y direction, and it's negative to represent downward acceleration. So here we just have the code in more depth. These are some initial conditions, and then the most important thing to note is that the proportionality constant for the drag force is 0 because there is no drag in this model. So here we just have the rest of the code and the graphs from the model. The most important thing is that the velocity is constantly accelerating downward, which is because there's only gravity in this model. So here we just have gravity versus tracker, and we can see how gravity overestimates the amount of acceleration downward, and we can say that that's because the drag force in real life will oppose gravity and make the downward acceleration less. So in the gravity and drag model, the code is mostly the same, except that we account for the drag force. So the proportionality constant is obtained by running the program until the final position is about the same as that given by tracker. And to account for drag, we can add the drag force to the net force equation. So here we have the graphs for the gravity and drag model, and we can see how the velocity versus time graph is slightly concave up, representing a non-constant acceleration. So here we have all three graphs, and we can see how the graph for only gravity accelerates at a faster rate than the other two, which illustrates how falling objects in real life are under the effect of more forces than just gravity. The tracker and gravity and drag are more accurate, especially towards the end. So some sources of error might include the inaccurate drag proportionality constant. It could be more accurate if we calculate it using the terminal velocity and the full formula rather than just estimating it. Also, there could be inaccuracies while using the tracker. If we used a longer video with more points, it would be more accurate. So out of the computational models, the drag and gravity model predicts terminal velocity because it's concave up velocity graph with drag. Has a decreasing slope, which implies that velocity approaches some constant value. So as velocity increases, the drag force increases, and eventually this will balance out weight, which will make acceleration equal 0. So if there is an initial velocity downward, the terminal velocity would remain the same because terminal velocity only depends on the fact that at some point the drag force will equal the gravitational force. And here we just have computational models to represent that. This is just the gravity and drag model, and we can see that in all cases where there's initial velocity and no initial velocity, they approach the same point at around negative 8.38.4. So overall, a falling object would have constant acceleration in a perfect vacuum. However, in real life, this is generally not true, which implies the existence of other forces. And through this lab, we saw how opposing forces affect the velocity and position of a falling object over time.